All right, so one last example in terms of finding the local extrema and the inflection point. So for this one here, we have the function f of x equals x times e to the power of x. Something that's maybe a little bit more interesting just because for this here, we have a power rule. This is not working. There we go. So power rule. So I'm just going to identify my two functions as I do usually. So if I'm multiplying f times g, and then I know that the power rule typically is f prime g plus g prime f. All right, going back to black. So we're trying to find the local extrema inflection points that we usually call the stationary points. These happen when the tangent at that point is horizontal. So if it is horizontal, therefore it means the derivative is equal to 0. So we need to do a first derivative test. All right. First derivative test. So deriving this, like I said, it's a product rule, which means we take the derivative of the first part, which is x. Derivative of x is just 1. And then times the second, which is just e to the x. No derivative needed. Plus g prime, so derivative of e to the x is e to the x times just f itself, which is x. So that's our derivative. Now we need to know when this is equal to 0. So I'm going to set it to 0 and factor things out a little bit. So we could factor out an e to the x here and be left with x plus 1. So with this, so there's two things that can happen. It's either you have e to the x equals 0, but guess what? This never happens. Never happens because whatever exponent you're going to put, it's never going to make this whole thing equal to 0. The other way you can think about this is by thinking about the graph of e to the x. So remember when you're finding 0, for example, for quadratic, then what you're doing is finding those 2 points here, right? So when you're finding when your function is equal to 0, it is actually finding the 0 or the x-intercept. So it's the same thing for e to the x. You're trying to find when it crosses the x-axis. And if you recall, when we graphed e to the x, it looks like that. Never actually crosses the x-axis. So because of that, there is no solution to this one. So our only thing that might happen in that case is to have x plus 1 equal to 0, which is fine if x equals to negative 1. So that here is our stationary point. Right, we know what stationary point we could possibly have. So the next thing I'm going to do is verify if the stationary point is concave up, down, or if it's a change in concavity. Because if it's a change in concavity, then it's an inflection point. The other two cases would give you local extrema. So let's do the second derivative. It's thankfully quite simple. So we're going to take the derivative of e to the x, so this first part here, which is e to the x. And then the derivative of e to the x times x, that's a product rule, which is quite annoying, but we already did it right there. We derived this function. It's the same, which means our derivative for this part should be e to the x plus e to the x times x. So I'm just going to put this down. Now, clearly, there's something I could factor. So we have 2 e to the x, so e to the x times 2 plus x. That's an e. Doesn't look like it, but it is. All right. So we have our second derivative. The last step is to go ahead and figure out on our number line what's going on. So the only possible point we have is negative 1. Its derivative is, of course, equal to 0. Its second derivative now is what the question is. So if we go ahead and substitute minus 1 in there, then we get f prime prime of minus 1 equals e to the minus 1 times 2 minus 1. All right, so clearly e is positive. 2 minus 1 is positive as well. So overall, this thing here is positive, which means we have that the function itself has to be concave up, which means that her point is a minimum. So our answer would simply be we just lost that. So we said this is up, this is a min. So answer is x equals to -1 is a local mix. Min is a local minimum. And that's it.